So let's take a look here. We have process mean as 10.7. Okay, standard deviation is 0.0868, and 3 standard deviation from the center is 10.4 here. 3 standard deviation beyond the average is 9.7. Okay, so this is your process limit. And we'd like to know what is the proportion of defect. Okay, proportion of defect. So the proportion of defect is not actually determined by those process limit. Instead, those are determined by the specification limit of the customers. Okay, customers. So customers spec limit here, 10.9 here. So let me use 10.9, right? 10.55. 10.55. So as you can see, the spec limit is actually within your process limit. You're actually making a lot of things, a lot of defective parts that is not fitting the requirement of your customer in here. I know it's a bit messy, but the key here is your spec limit is within the process limit. We'd like to move that spec limit outside of the process limit. That is the ideal case, which in this case, that is not. So if you look at the total proportion of defects, so you have 2 defects coming from 2 different areas, being too small, being too big, and you combine these, this is a proportion of defects. You multiply 1 million, this is your DPMO. Okay, so DPMO is actually very huge. This is not a very capable process. That is the verdict. So if you look at the distribution, it approximately normal, right? If you can approximate it. So a lot of times we are approximating it because nothing will be exactly normal. So let's take a look. How to evaluate process capability the only information needed to conduct a process characterization study is the mean, standard deviation, and the histogram of sample measurement, which just like what we did. If the distribution is approximately normal, then we know that 99.73% of the observations will fall within 3 standard deviation from the mean. Okay, so you looked at it. We have already reviewed it using the empirical rules. Okay, so this 3 sigma range is things that we are looking for, and mu is the process average. So from lower to upper, you have a 3 standard deviation here, another 3 standard deviation here. Then we have total 6 standard deviation in here. So you may be tempting to say this is a 6 sigma, but this is not a technical definition of 6 sigma. Okay, but we're only looking at 3 sigma quality in here. I will explain what 6 sigma means when we move on to the next chapter. So here, this is how you utilize the histogram. So we know how to utilize the average and standard deviation to identify the probability of defect. And sometimes the histogram itself can provide a very important information. So things like that, a lot of the processes are falling within the specification limit, which is actually a good thing. Okay, which is a good thing. You don't actually make something outside of specification limit. Here, if you look at the B, right, this is close. This is more spreaded than A, but it's still within the specification limit, which is a good thing. Okay. However, starting from this one, we're seeing things that are outside of spec limit, which to us is not a good news. Again, this one this is something called not centered. Okay, the process is not centered. The centered process means that center of the process is situated exactly in the middle of a spec limit. Okay, like this one looks like it's centered, but this one is clearly not. Also, the huge chunk falling outside of the specification limit. So it will not generate defects because those are being too small, but they will generate sufficient amount of defect, substantial amount of defect because of being too big. The same problem here. For this one is opposite. They will make a lot of smaller parts. There are a lot of defects because they're being too small. This looks like they're piling, two different things together. And it means that they may have changed something in the middle. Therefore, you're seeing two distinct patterns here. Okay, again, this one too. We're seeing two distinct patterns. This may be made using some leftover materials that is not the same with this. That ended up become a huge amount of junk is generated. So again, this one is not centered. This one is not centered. It doesn't tell a whole lot of useful information from here. So the histogram can tell many underlying characteristics about the processes. Okay. However, there is a shortcoming of a histogram. Histogram is rather static. It's a snapshot of the current process. It does not tell you whether the process has changed or not. For example, if you look at here, it's clearly, the control chart here is clearly operating based on two different average here. Okay, ever since from 16, it looks like the average has changed, but you can't really tell by just looking at the histogram. So we use histogram to assess the what is the overall distribution of the process, but we can't really use histogram to detect whether the process has changed or not. Okay, so here I'm going to be demonstrating some more cases. So lower spec limit is within the process limit, which to us is a good sign or bad sign. What do you say? It's actually a bad sign because you're making a lot of junk that does not meet customers' requirement. These will be categorized as junk. Okay, but if you look at the next diagram, because the spec limit is way outside of process limit, okay, a lot of parts you thought that was a junk, but they're still can satisfy customers' requirement. Okay, that is the story here. Okay, can you see the difference here? One has a spec limit before the process limit. The other has a spec limit outside of the process limit. This is the ideal situation. The second drawing is the ideal situation. We want to have a spec limit way outside of a process limit. Okay, so that even the products that I think is junk is actually a gold. Customer can still take those. Okay, this is what we're arguing here. This is demonstrating the process that is not centered when we compare it against the specification limit. Spec limit is here, and your process is here, right? So the process average is not centered when you compare it against the spec limit. Okay, it will generate a lot of junk, a lot of oversized junk. So for this one, it will generate a lot of undersized junk. Okay, these are different scenarios can happen when you compare your process characteristics with the specification limit. So to capture that, we use a series of indices to formalize what we have confirmed visually. So to determine the process is capable of meeting the specification limit. So let's begin with CP. Okay, CP is measuring whether the spec limit, starting from lower spec, over spec limit, whether they overlaps with your process perfectly or not. Okay, if these two, this is process limit, this is another process limit, this is upper, lower, right? If these two overlaps perfectly, you'll be ended up getting CP that is exactly 1. Okay, 1. But even better, if your CPL, upper CPL and if your process limit, lower process limit and upper process limit is even narrower, which is the key, is narrower the specification limit, you ended up getting CP that is larger than 1, which is very preferable. However, if you are seeing something like this, your upper limit and lower limit, it's much wider than the spec limit. It's very likely that, it's not very likely, you will certainly generate a lot of junk from both ends. Okay, so CP can tell you whether your process limit is actually narrower than the specification limit. Okay, so if you look at this case, we looked at the first case. The first case has a lot of junk in here because the spec limit is within the process limit. As you can tell, the CP is less than 1, indicating this is not a capable process. However, if you look at this guy right here, okay, you see the spec limit is outside. Spec limit is outside. So, as you can expect, we have CP is larger than 1. Let's take a look at these two cases. When it is not centered, when the process is not centered. We look at this example earlier, we studied that it will generate a lot of oversized junk, but still it gives you greater than 1, which is indication of capable process. Again, this will generate a lot of undersized junk. It's not quite captured in the CP. Therefore, we need a better way to capture that information. Okay, so the better way to capture that is you are, sorry, I think I need to correct this here. We need to correct it back to 3. We are measuring the upper spec limit, lower spec limit separately. Okay, so we'd like to make sure whether in the upper part, okay, this part, whether you have enough standard deviation from center to the spec limit. You're also measuring it separately for the lower end, whether there is enough standard deviation until it gets to the lower specification limit. If you observe this formula closely, that's the story it is trying to tell you. So they are measuring the specification limit, they're measuring the capability separately on each end. Okay, ideally we'd like to have at least 1 on each end. Okay, so as you can see, right, as you can see, all these things. Okay, so these two should not be a problem, but these two should be a problem. As you can see, in the lower part it is capable, it is not capable in upper part, which confirms my earlier statement regarding this process, which it will generate a lot of oversized junk. Okay, again, in an upper part this is capable, in lower part it is not. Okay, again confirms my earlier statement. So the truly useful capability index is that when you pick the smallest between these two, so when you pick smallest between these two, right? When you pick smallest one between these two, that becomes the truly useful capability index. So when you say 0.9, the one thing you can tell is, oh, this is not a capable process. The next thing you can tell is, hey, this process is not centered. Okay, that is one thing you can tell from that. And there is a different way of calculating this capability index in addition to, calculating 2 items and pick the minimum. If you look at this formula closely, this is measuring the this is measuring the relative location of your process average. Okay, this is measuring the relative location given your lower spec limit and upper spec limit, and it is calculating the relative location of your process average given the true target. Okay, and using that value to estimate the value of CPK. Okay, I just used the verb estimate. Okay, not to forget, so far, whenever we try to calculate the capability index, we'll be using sample result. Whenever we use a sample result, that means it is just an estimation. It means when you draw another group of sample to estimate the capability index, it may give you different result. So for that reason, it is important for us to put a confidence interval. So if you remember, whenever we're trying to measure the true, whenever we're trying to estimate the true average, we used x bar plus minus margin of error. For the same reason, for the true capability index, we also like to use margin of error. Okay, the size of margin of error is this. It looks complicated, but most likely you'll be ended up looking at the formula to do the calculation. So please don't worry too much about it. So it's likely that this value is determined by the underlying distribution for the CPK, which a lot of times we don't have knowledge about. Okay, so that's the reason why this looks like very monstrous. But I'd like to just remind you what that is for now. Okay, so take a time to calculate these. I've already calculated. These are the capability index individually. So the only capable process in here is this guy. Okay, so what happens to these guys? What is your recommendation for fix? So the recommendation for fix is usually that you either have to recalibrate your system so that it will generate more even part. Okay, we'd like to have a more evenly distributed. I'm sorry, we'd like to have a system that generates parts in a smaller standard deviation. Okay, meaning that part-to-part difference should not be that big. Okay, for this is okay, so that we don't worry about this. So for this one, we need to, first thing we need to think about is that we need to readjust the average by utilizing some better mechanics or replace some parts. So over time, machines do change. So in this case, what you need, because your spec limit is here, so you'd like to target center. So it means that you need to adjust your average to the left. You need to shift your average. That's the term we use. So for this guy right here, I believe this is also not centered. So therefore, you want to shift the average to the right. Okay, so in that case, that is the first step. We also have to recalculate the capability index to see whether the after shift, the process is still capable of meeting the specification limit. Okay, so these are more conceptual stuff. Before I conclude, this will be another question that goes into your homework number 5. I want you to think about this. Okay, we have studied Taguchi loss function, and do you think the capability index approach considers the very issue that Taguchi loss function is trying to address? Okay, think about that. Of course, you need to think about this first. So Taguchi loss function is trying to address what issue back in those times, and whether the capability index approach addresses that issue. Okay, so this concludes the my talk for these 2 sections. I will leave you some assignment to work on. Thank you.